In this lesson, we are going to continue our look at open sets in a metric space. So you should be able to tell me in this moment what a metric space is, when a set in a metric space is open, what a neighborhood is, and what an epsilon neighborhood is. You should also be able to tell me that any metric space is open, as is the empty set, and also any union of open sets is open, and any finite intersection of open sets is open. So all of these notions should be familiar to you. Let's start to add to this list. Okay, so I have two quick definitions for us to look at on this slide, and then we will work through several examples. So let's just run through the basic ideas here. We are working in an unspecified metric space. You might be tempted to picture R2 like the board, or you could picture a discrete metric space. And again, in a few minutes, I will bring in actual examples. In this metric space, consider a set A, which is not necessarily open. So this is just a plain old set in this metric space. We say a point X in A is an interior point if around X you can find an open set that is contained within A. So I like to imagine, here's A, could be open, doesn't have to be. Here's X. X is an interior point if I can find an open set U. So let's say this is open, which contains X, but which is contained in A. You'll notice in this picture that I gave you kind of a funny shape. That was on purpose just to emphasize that U here is just any open neighborhood of X, which is contained inside of the larger set A. It doesn't have to have the form of an epsilon neighborhood, but it's often helpful to give it that form. So you could equivalently rephrase this definition to say that there is an epsilon neighborhood around X contained in A. That definition would also work. We just won't require it. So here, A is whatever it is. I'm saying that X is an interior point versus if we just kind of associate to this picture notions like this point here is right on the edge. Let's say this is Y. In my drawing, this does not look like an interior point because we can start to imagine what open sets around it would look like. And no matter how I try to sketch open sets around it, I can't find one in my picture which stays inside of A. Okay, so notice in this definition that we're saying there exists an open set U. It's not enough for Y for me to say this open set doesn't work. I would have to argue that no open set contains Y and stays inside of A. All right, so that's the notion of an interior point. And then what we can imagine doing is collecting all of the interior points for which X would be part of that collection. And that collection of points forms a set that we call the interior of A. All right, let's put these two definitions into practice. I have 5 examples for us to look at here. In each of these 5 examples, we're being asked to identify the second definition that we just learned. So we're looking for a set, which is the interior of the given A. The first one, we are looking for the interior of Rn, where here it's implied, I should probably state it, but it's implied that the metric space is Rn with the Euclidean metric on Rn. Then examples 2, 3, and 4, similarly, I'm giving you subsets of the real number line. If I just give you a subset of the real number line and I don't say anything else, it's a little bit lazy on my part, but my intention is that the ambient metric space is R and the associated metric is the Euclidean metric. So it's like R or Rn without further precision refers to the usual Euclidean space. And then in example 5, you see that we will be working in a discrete metric setting. Okay, let me do the first one. And then I would like for you to pause and think about examples 2, 3, 4, 5 if you like. Take them as far as you can. So for this first one, we are looking for the interior of Euclidean space Rn's. I'm going to give you 2 possible routes you could take. They're going to arrive at the same conclusion, of course. You can pick your favorite. You could come up with a different one. For any point in Rn, here the metric space is Rn, and we know that every metric space is open. So we're saying X is already contained in an open set. Kind of clever, but you can say X is in Rn. which is a subset of Rn. By writing this, what I'm doing is I'm saying this first copy of Rn is the open set U from the definition, and then the second copy is just pointing out that the set we're assessing is A. So if you have the definition from a moment ago handy, X is contained in an open set U, which stays inside of the larger set A. Might be worth mentioning in this moment that when I write subset like this, I never mean strictly proper. So here we don't have proper containment, and that's fine. Okay, I like this. If you don't like it, if you would want to come up with something that feels like U is a little bit smaller, what you could do is say for any X in Rn, X is an element of a neighborhood around X of radius 1. We proved that all epsilon neighborhoods are open. So here, instead of trying to be too general, which is just not necessary, so there's no reason to say for any epsilon greater than 0, you can just pick one. We just need to find one U that works for X. So I'm going to say take the unit radius and draw an open epsilon neighborhood around X that contains X, and of course it stays inside of Rn, it's not going to leave. So here, this is our U. You could, of course, do something different, but both arrive at the same conclusion, which is that the interior of Rn is Rn itself. All right, let's pause and think about the others and take them as far as you can. The answers for 2 and 3 are the same. So for both, the interior is the open interval from 0 to 1. Let me sketch the argument why. I think as I do so, I will basically say the proof out loud. But suppose this is the number line. And let's first just address this set. So the open interval from 0 to 1. Take any X in this set, say this one. I need to establish that there's an open set U containing X, which stays inside of the open interval from 0 to 1. There's a prescriptive way to do this. What you can do is set up an epsilon neighborhood where you say what the radius is. So consider the distances between X and 1 and X and 0. Take the smaller of the two. If you like, you can cut it in half, but I'm just going to take my radius as the minimum distance between X and 1 and X and 0 in this picture. That looks like this distance. Then this defines an epsilon neighborhood around X, which will serve as U in the definition of an interior point. So therefore, the interior of this set is that set itself. Let's now look at example 3. I'm going to take my picture and just change it a little bit, like so. A point is an interior point of the set A if it belongs to A and there's an open set U containing that point which stays inside of A. So there I've just tried to restate the definition of an interior point. What I wanted to lift up there is that the point must belong to the set. At this moment, we have assessed every X between 0 and 1, and for each X, we can construct a U that works for the definition. The only points we haven't assessed yet for this third example are the endpoints at 0 and 1. Okay, so let's consider those. You probably see the conclusion kind of instinctively right away, but I do want to mention something important here. Consider 0. I don't want to give U a prescriptive form quite yet. So imagine that I have some open set containing 0. I don't even want to argue that it's inside of the interval that we're considering. Just imagine U is some open set containing 0. Because U is open, there must be a positive epsilon that creates an epsilon neighborhood around 0 inside of U. So it's like, if I say I have an open set U, I also have an open epsilon neighborhood. That means I can argue with this prescriptive form. Okay, so all that to say, consider any epsilon greater than 0 and draw the epsilon neighborhood that you would form around 0. So for any epsilon greater than 0, the epsilon neighborhood around 0 actually has a form we can write down. It has negative numbers in it, so it's not going to stay inside of this set. So let me actually write, this is not a subset of closed interval from 0 to 1. I said closed, but we haven't actually defined it yet, but we've called these closed intervals for years, and we'll keep doing so. Okay, so I'm saying here that no epsilon neighborhood will form an open set of 0 which stays inside of the set we're assessing, and that's enough. Because I can't form open neighborhoods of this form, no general open set U can work. To reiterate, in case you missed the argument when I started it, if a general open set U works, such a neighborhood must also work. Because around any, like if you have any open set U and a point in it, by the definition of open, there must be an epsilon neighborhood around this point which stays inside of U. So if this can't work, this can't work. Okay, I think I've probably spent too much time on this point. Let me pause again, and if you haven't done so, go ahead and think about examples 4 and 5. All right, for the set of integers, hopefully you got the empty set. To see that, we have to consider neighborhoods around integers. Let's just take this one and call it n. Once again, if I can show no epsilon neighborhood works, that's enough. So imagine you take any epsilon neighborhood, could be small like this, or you could pick something really large that picks up other integers, that's okay. We know that any neighborhood like this is going to have irrational numbers in it, right? So no epsilon neighborhood around an integer can contain only integers. So no integer satisfies the definition of an interior point. Those are the only points we needed to test. Therefore, the interior is empty. Okay, let me erase this and we will finish up this set of examples with this discrete metric space. At the beginning of the lesson, I said a bunch of terms that I expect you to be able to define in the moment. The discrete metric should have been on that list. And when you think about the discrete metric, you should remember things like any subset of a discrete metric space is open. So what we can say is for any x in A, that's supposed to be an A, for any x in A, x is in A, which is a subset of A. And notice that's a lot like how I started with this example. So here, this first copy of A is U, and then A here is the set we're testing. So we're done. If X is a member of a set in a discrete metric space, it's a member of the interior of that set. Put it all together, and the interior of any set in a discrete metric space is that set itself. If you don't like this, let me give you a second version, which again mirrors the second version for our first example. For any x in A, x is in the neighborhood of radius. You could go all the way up to 1 if you like. Around x, you can make that 1/2 if that feels a little bit more sure. This is correct though, because this epsilon neighborhood of radius 1 consists of all of the elements from the discrete metric space whose distance to x is less than 1. There is only one such element, x, which is a member of A. So this single element set is a subset of A. Here, this is the U. So it's kind of neat. If you take an element in a discrete metric space, it forms its own singleton set, which is an open set. That feels really different from, say, working in Euclidean space. So this is another nice way to realize that if you are looking at a subset of a discrete metric space, it is its own interior. Okay, having gone through these 5 examples, let's collect some facts, and then we will prove some results. All of these interiors are open. So this is open, these are open, open, open. When the original set was open, it was its own interior. So the interior of Rn is Rn, same for the open interval from 0 to 1, same for this one. Okay, so we've got interiors are open. They are the set when the set was open. So the interior of A is A when A is open. Let's start to formulate those now into results and we will prove them. All right, the first result we are going to work through isn't maybe the most immediate conclusion from the previous exercises, but we need this to state two observations that we basically just made out loud. So this says that the interior of a set A is the union of all open subsets of A. I want to restate this, and I don't want to keep writing out the union of all open subsets of A. So let's denote this union by capital B. All right. This sounds like a fact, but of course in math, when we state facts, we need to check, like, are there hypotheses and conclusions here? We are saying the interior of A is this set B. This is a statement about set equality. So in other words, we could say this is a theorem that we are about to prove, which is int A equals B. B defined this way. Okay, so be careful not to just read things and think, oh, that's just a fact I'm allowed to know. No, this is something that we're going to prove. I'm going to say the proof out loud, but I'm just going to give a sort of casual presentation of it. This is a set equality proof. I want to show two sets are equal. Take a moment to say out loud, how do you prove two sets are equal? The most classic way to establish set equality is to show they have the same elements. So in other words, if X is in the interior of A, then X is in B, and vice versa. If X is in B, then X is in the interior of A. So when I say sketch here, I don't mean I'm going to draw something. I just mean I'm going to go through kind of the outline of the proof. So we want to show X is in the interior of A means that X is in B, but also if X is in B, then X is in the interior of A. So it's an if and only if proof. Okay, again, I think this is a full proof. I'm just not going to write complete sentences. So we have, let's start moving left to right. Suppose X is in the interior of A. By definition, that means X is an interior point of A. So we know that around X, there's a neighborhood U, which is open, containing X, but staying inside of A. All that to say, X is in U, which is a subset of A. Here, this is open. This is not how you would write it in a formal proof. You would say, if X is in the interior of A, then there exists an open set U containing X, et cetera, et cetera. But for the outline, this is nice enough. But then X is in an open subset of A. Such a subset is exactly what we're collecting when we form this union defining the set B. So if X is in one of these types of sets, then X is in any union containing that set. So X is in B. It's not a complete sentence, but I just can't not do the period. I think we can actually just reverse the order here, but let's do it out loud. Suppose now that X is in B. That means X is in the union of open subsets of A. To belong to a union, you need to belong to one of the members. That's what we're going to identify as U. So if X is in this union, X belongs to one of the members of the union, but then X is situated inside of an open set contained in A. That puts X in the interior. Okay, so again, this is just an illustration of the proof, but I think you get the point. I said this isn't the most immediate conclusion that you probably came through working through the 5 examples that we just looked at, but what does this tell us about the interior of A? It gives us a property. Do you see it? We are now characterizing the interior of A as a union of open sets. Any kind of union of open sets is open. So let me see if I can squeeze it down here as a corollary. Something we did observe with the 5 examples is that all of those interiors were open. We've now shown that because any union of open sets is open, including this one. Okay, so let me step aside. You can finish thinking through this, and then I have one more result to establish. All right, let's wrap up with this if and only if statement. This is another corollary of the result we just proved. A is open if and only if it is its own interior. That was something that we observed. The interior of Rn was Rn. The interior of any set in a discrete metric space is that set itself. So that kind of pattern that we spotted is summarized here with this statement. This is an if and only if statement, and you might be able to take what I'm about to write down and roll them into just one kind of if and only if chain like what we just did. However, both directions are pretty short, and I think it's a little bit more organized if I just do kind of a classic if and only if proof. All right, so uh, let's go left to right. Suppose that A is open. Two ways jump out at me to proceed. One is to realize that if A is open, then it belongs to that union B that we were just looking at. However, I've erased all that notation, so I'm going to take option 2 here. Then for any X in A, I'm going to write this for like the third time this lecture. X is in A, which is a subset of A. So X is in the interior. Thus, A is a subset of the interior. Okay, let me pause here and then we will finish this direction. Suppose A is an open set. Then for any X that you pick in A, X is in A, which is a subset of A. I hope you recognized I was doing that construction here where this middle term is actually the open set U from the definition. So therefore, X is in the interior of A. What we've shown is if X is in A, it's in the interior. That means that A is a subset of the interior of A. However, it's in the definition of interior that the reverse containment is also true. Since the interior of A consists only of points which originally belonged to A, we know it's a subset of A. Here we have reverse containment. That makes these two sets the same. You could probably write this more concisely. And again, you could appeal to the B union that we had in the previous statement. The other direction is faster. I think I can fit it down here. If A equals its own interior, we just said that an interior is open because it's the union of open sets. It's a union of open sets. So if A equals the interior of A, then by what we just talked about, A is open. Since we characterize the interior of A as a union of open sets. Okay, so that wraps up this lesson on interiors. One thing I wanted you to take out of this is that, looking at those examples that we worked through, you may have been able to spot immediately what the interior was just by saying the word interior out loud. So when we work through topological notions like interior, and as we'll meet later, boundary and closed sets and closure, they are often given names that reflect our intuition. So if I just draw a set, and I say, what is the interior of the set? You probably would want to say this because the word interior was well chosen. I'm saying this to tell you that your instincts are often right, but always keep the definitions handy. Certain metric spaces, like the discrete metric space, it might not have been immediately obvious what the interior of such a set would be because it's not going to take this shape. Similarly, when you first thought about the integers, you might not have had like an immediate intuition like you would for, say, the open interval from 0 to 1. So while these words that we use in topology are often very illustrative and often do align with your expectations, keep the definitions like stored in your memory and make sure that they are precisely phrased. Okay, I'll wrap it up there. Thank you for your attention.